We're going to shift gears here as to topic, and we're going to get into another topic that Jim Elsner will introduce to you. Jim has his PhD in meteorology from the University of Wisconsin. He holds the Earl and Sophia Shaw Professorship in Geography at Florida State. He's president and CEO of a company called Climatex, a company that develops software for hurricane and tornado models. He's done extensive work in hurricane prediction and risk reduction, and he organizes a biennial summary of the topics of hurricanes and climate change. So the title of Jim's talk is going to be Inspired by the Work of Edward S. Epstein, a Model for Predictive Hurricane Climatology. You have 30 minutes.
Well, thank you, Bob, and
How long would you like on the timer?
maybe
Sorry.
15 minutes. Yeah, thank you, Bob, and I'm honored to be here speaking about what inspired me in some ways, and my career path was inspired by Edward Epstein. I never met him, but so my recollection is reading his papers, and in particular, I'm going to focus on his AMS monograph, his 1985 monograph. And I begin with the quote, "The goal is to produce useful predictions that are consistent with one's best judgments and to allow consistent revisions of those judgments as data become available." Again, that was in this very thin but very powerful AMS monograph that was published in 1985. So the problem is, when I first became interested in hurricane climatology in the early 1990s, I ran across a lot of information about past hurricanes from a variety of sources, including instrument records and handwritten accounts. Written accounts, of course, were less precise than the records from the instruments, which of course tended to become even more precise as the instrument technology advanced. So the question that I had to address was, and I had to deal with, was how was I to make use of all this information in a meaningful way? We often hear climatologists say, well, I started my study from this year because the data before that year were not as precise or less reliable or some other. But Edward took a different approach. He basically said that you really want to use all the available information, okay, and discount in a meaningful way, in a way that makes sense, this older information that's less precise. And so that, when I read that in this monograph, that's when the hairs on the back of my neck started to tingle. And I realized that he had put together a solution to this problem. Now, he wasn't studying hurricanes, but the solution for my problem studying hurricanes was in this book. And it was based on the Bayesian method. So I'm going to walk you through this, and maybe you can see some of his genius as I walk through this. And what was really remarkable is the clarity at which Edward wrote. Okay. Again, I had never met him, so it was something that just reading the words, he was very meticulous and very clear. And as a young graduate student, it was very easy for me to follow what he was doing. So in fact, I wrote a paper with a graduate student back in 2001. And that paper was based on what I gleaned from the solution to the problem of using older, less precise data that Edward had come up with. So in fact, that paper led me to issue a forecast. It was a climate forecast. And the forecast was issued July 1st, 2001. At the time I submitted the paper, maybe at the time it was accepted. I should probably say it was accepted. The paper was accepted. And so it was a 30-year forecast. I was making a 30-year climatological forecast. I was using all the information that I had available to me. And so you can see the forecast there, very simple forecast. I forecast the U.S. hurricanes, and I said there was going to be 50 hurricanes over the next 30 years. Now in 2001, in July, the next 30 years was 2001 through 2013. Hurricanes don't come until after July in general. So the total so far, well, 2001 through 2030, the total so far is 21. Okay, so this is keeping track of how well this forecast is going. I forecast 18 major hurricanes. We've had 7 so far. And the model also then forecast Florida hurricanes. Forecast 20 of them, we're up to 7. So what I'd like to show you today is how did I use the work from this book, Epstein's work, to solve my problem and come up with this forecast. Well, if we consider the arrival of hurricanes on the coast of the United States, or any coast, as a stochastic, which you can read as random process, where the annual counts are described as a Poisson distribution. Okay? So this Poisson distribution then is described by a single parameter we call lambda, which represents the rate at which hurricanes arrive on the coast. So if we know lambda perfectly, the Poisson distribution will tell us what can we expect in terms of the counts, what's the probability of 0, and so on. So knowledge of lambda allows us to make statements about future hurricane frequency. Now, since the process is stochastic, your statements will be given in terms of probability, as they should. So for example, the probability of H hat hurricanes occurring over the next t years, for example, t is 1 or 5 or 20, etc., is given by this density of the Poisson distribution. The exponential of minus lambda times t multiplied by lambda t raised to the h divided by h factorial. So we can calculate that density for h equal to 0, 1, and so on. And gamma is constrained to be greater than 0. It's the rate. You can't have a negative rate of things. And t is greater than 0. So count a number of years. So this hat notation is used to indicate future values. So the problem I faced is that the knowledge about lambda can come from written archives and instrumental records, kind of to simplify the problem a bit here. So you want to use as much information as possible before inferring what might happen in the future. Now, this might not be so important if the future is just next year. But if you're trying to think about a long scale, the long-term climate, then it's very important to think about getting all the information from as far back as possible. So this requires you to treat lambda as a parameter. It's not a constant, not a fixed constant, but as a parameter. And lambda then, being the rate, can take on any positive value on the real number line. Okay, so lambda is any value, any positive real number. The count, of course, is an integer, but lambda, the rate, is this continuous variable. So one way to express your judgment about lambda is through the gamma distribution. So the numbers used to estimate lambda from a set of data are the time interval t prime and the number of hurricanes h prime over the interval. Okay, I'm going to use the prime notation to indicate estimates of these parameters based on the data, or the current data. So this prime here, in this case, actually the prime indicates the prior or early information. Double prime will refer to later information. So for instance, observations from hurricanes recorded since 1851 indicate there were 15 hurricanes over the first 10 years of the record. Okay, so you can say, well, the rate is 1.5 over those 10 years, but we could have missed a storm, or we could have misclassified a storm. So there's an uncertainty about that. So let t prime be 10 and h prime be 15. And now you can do this for yourself. And this is one of the things that Edward was very good at, is being very clear It was easy to follow. In this modern age, we can be clear and we can allow people to follow us by giving them the code and the data so that they can see exactly what you're doing and how you're doing it. So if you want to do this, you can download the slides here from that link on the bottom, and you can read in the hurricane count data set that was used to make this forecast. So again, this is using the R language, and I read in a data frame called H, and then I sum for the first 10 years, the first 10 rows, and I get a value of 15. So the gamma distribution of possible future values for lambda is given by this density where where t prime is raised to h prime times lambda raised to the h prime minus 1 divided by the gamma function evaluated at h times exp minus lambda times t prime. So that density of the gamma looks very similar to the density of the Poisson. In fact, they are a conjugate distributions. So with the expected value of lambda hat given by the number of hurricanes, h prime, divided by the interval over which you're counting, t prime, and we're, again, gamma of x is that gamma function. So if the probability density on lambda hat is a gamma distribution with initial prior parameters h prime and t prime, and the numbers h and t are later observed. So we just took the first 10 years to get h prime, t prime, but then we observe h and t later on, then the posterior density of lambda hat is also gamma, with the parameters simply summing up. So we have h plus h prime and t plus t prime. And we have a posterior distribution by just adding the parameters. And so this is what's called a conjugate prior for the Poisson rate lambda. So this gives you a convenient way to combine these earlier, less reliable pieces of information with what we accumulate later. So you simply add the prior parameters h prime and t prime to the observed numbers h and t to get the posterior. But how do you estimate these priors? Okay, so you have values, right? You have, let's say, 10 hurricanes or 15 hurricanes over 10 years, but they could be low or too high due to missing or misclassified information. And so what Edward was able to come up with, and this is, again, I think what tingled my neck hairs the most, is he said, let's use a bootstrap technique. So we can sample from our sample, and I think this is a really clever idea of what he did. So for example, how do we do this in R? We're going to use the bootstrap function. So we're only interested in hurricanes before 1899, and we'll call those early. And then we're going to generate 1,000 bootstrap samples, and we're going to save them in BS. And so then we can get a 90% bootstrap confidence interval on the mean hurricane rate prior to 1899 by using the quantile function. And so even though the likelihood estimate for lambda based on the data is 1.5, we have a credible interval. We can think of it as a credible interval of 90% between 1.39 and 2.12. So it's really this uncertainty that arises because we're not sure about those earlier records that we want to use in our model. So you can't say with certainty what the true hurricane rate is, but you are willing to admit a 5% chance that the true rate is less than 1.5. This is how we interpret that credible interval in the Bayesian sense, and a 5% chance that it is greater than 2.12. So this appraisal about these early American hurricane rate, you need to obtain, given this appraisal about the early American hurricane rate, you need to obtain an estimate of the parameters of the gamma distribution. So you start by creating an objective function. So we have quantiles, we have any quantile we want, so we just want to set up an objective function that gives us the parameters of that gamma distribution. And so this is how we did it in R. And so we end up using this procedure with an H prime of 61.7 and T prime of 35.4. So think about this. Think about what's happening. You have data before 1899. It's uncertain. So we don't want to use just the likelihood, the mean. You want to have an uncertainty. So the information content, according to Edward, is that we really have 61.7 hurricanes over 35.4 years. Okay? And that's the information we want to move forward in time. And then of course we can think about the hurricanes since 1899. Now we just sum, and we call those late. So years greater than 1899. We have a H and we have a T. And so there are 187 hurricanes over 112 years. So these are what you call your likelihood statistics. And then as explained, the posterior parameters are simply a summation of your prior parameters with your likelihood. And we'll call those double prime, H double prime equal H plus H prime, or 248.7 hurricanes over 147.4 years. So note that although the likelihood parameters H and T must be integers, the prior parameters can take on any real values. Since the prior likelihood and posterior are all in the same gamma family, we can simply use the d gamma function to compute the densities. So here's your result. The green line is your prior. That's your information about the hurricane rate at the U.S. coastline before 1899. It's the green line. It's wider. It's flatter. It's more uncertain. Then the likelihood is the red, and then your best estimate of future is your posterior in black. Okay. And so using Bayes' rule. Okay. But of course, you're not really interested in the mean. You're interested in what might happen over the next year or so. So you really want a predictive distribution. And we use the predictive distribution, and we can work that out in the same way. Again, Edward explains this just using the predictive density on that gamma. So the mean and variance of the negative binomial, that's like the negative binomial distribution, is given by t hat. So if you want to know over t hat is the number of years in which you want to make your prediction, you multiply t hat by h double prime over t double prime. Again, those are from the posterior, and your variance is given by the mean multiplied by t hat plus t double prime over t double prime. So note that the variance of the predictive distribution is larger than it would be if lambda were known precisely. So you wouldn't have that t hat in there. So if you're interested in the probability of a hurricane next year, then t hat is 1 and small compared with t double prime. So it makes very little difference. But if you're interested in what's going to happen over 20, 30 years or so, which is what I was, it's quite important. So this is the predictive distribution. The gray histograms indicate the probability of observing that many hurricanes in the next 10 years based on the model. Okay? So the probabilities are going to be low for any given count, and then the black line is the cumulative distribution, the probability that it's less than, let's say, 25 hurricanes. Okay? So this is the information contained in the posterior distribution. So we can do this for t for predictions out 10, 20, 30, any number of years we want. And now I'm looking at the probability that H is greater than H. So insurance purposes, you're always interested in worst case scenarios. So what's the probability we're going to get more than 50 hurricanes in 20 years? This answers that question. So in summary, with Edwards' method applied to my hurricane data in July of 2001, I predicted that the number of hurricanes over the next 30 years would be 51. These are U.S. hurricanes, of which 18 would be major, at category 3 or above. The approach outlined in Epstein and adopted for what I was doing is a rational, coherent foundation for incorporating the available information, while accounting for the fact that these earlier records have more fuzziness about them. So it could be used to account for influences of climate change. Records influenced by recent changes can be given more weight. We can think of those as the likelihood, than records from earlier decades. And my final words are reproducibility. Now, in Edwards' time, the idea was to write clearly so people could follow what you were doing, what you meant. And today, I try to emulate Edward by making my research reproducible. So the code used to produce the slides for this presentation are at that website. And thank you for your attention, and I'd like to give my best regards to the family and friends of Edward Epstein here. So are there any questions?
Floor's open for questions.
Did you compare what your prediction, show what your prediction came out with using the other data versus without using the other data?
Yes, we did in the paper. We compare them. So what's the information margin on using the older data? Yeah, we can do that. I didn't do it in this presentation, but it's in the paper. Yeah, I mean, when you get out that many years, it really doesn't have that. You could see it in the posterior. It was shifted a little bit. So the answer is in that posterior shifted relative to the likelihood. So, and that difference accumulates if you're making a long lead forecast. I have copies for the family of the slides also, if you'd like.
Thanks. Okay, the next item is a panel discussion, and if the members of the panel want to start coming up, while they're doing that, I want to say that this little book that Ed wrote and that Jim showed you and so on is really a gem. And in particular, the introduction. If you've never got a hold of that and read the introduction, it's really good. One of the things in there, you know, he says probability, the language of uncertainty, and I've seen those words in other places now since then, in Dan Wilk's book, for instance, and so on. And it is so clearly laid out here. Even though Ed was a Bayesian, he recognized that there was a place for the relative frequency concept, and it's in here, and not all Bayesians do that, and so on. Very good introduction. Dick?
Well, we're going to cover now a period from when Ed went to Michigan, and this period when he was at NOAA headquarters and also at the Climate Analysis Center, and also from an international point of view. We have 4 guys here that know a lot about that, and they're going to try and share it, and we're going to try to do it along the time frame going from the 60 on forward, and that's how we determine the order. And I know that Gene Beerley and John Lease have to decide just because there's some sharing going on, and I think they've already done it, so I'll turn it over to them to start. Pardon?
Some power in the mics.
The-
Is it leaving? Is it really? Can you hear me in the back? Can you hear me in the back? Yes. Okay, that's fine. With my voice, you need that these days. It's really a privilege to be here today and talk about Ed and some of the interactions that we've had over the years. Turns out that as Ed was finishing his PhD in 1960 with Dick, that he received an offer from Wendell Hewson at the University of Michigan offering him a faculty position. So in 1959, and did I say 60 to start with? That's probably bad, but 1959, Ed actually joined the faculty at the University of Michigan as an instructor in the Department of Civil Engineering in the School of Engineering. Immediately, as soon as Ed got there, he started designing a course that used the computer at the university and applied to meteorological problems. He invited all of the grad students to sit in on the course, and I did that, and I was actually dumbfounded on how much that computer really helped in solving some meteorological problems. Not long after, it actually created a graduate course in statistics that required all of the students taking the course to be able to program the university's IBM 650 computer. In 1963, Ed was invited to become a scientific advisor to J. Herbert Holloman. J. Herbert Holloman was the first Assistant Secretary of Commerce for Science and Technology. One of Holloman's jobs, among his international activities, but among his jobs, was to find a new chief of the Weather Bureau because Francis Reichelderfer was going to retire in 1963. So Ed was asked to think of some names, and he gave Herb Holloman the name of Robert M. White. Holloman, being very careful, took a look at names and White's, and as it turns out that on October 1st in 1963, Robert M. White became the chief of the U.S. Weather Bureau, thanks to Ed and his suggestion to Holloman. Also in 1963, the Department of Meteorology, which had been formed in 1961 in Ann Arbor, decided that they were going to really form a department. And so Axel Van Nielsen was asked to become the first department head in 1964. Ed and Axel got along really quite well. In fact, when Ed took his research plan and talked to Axel about it, his research for STP, Axel was so taken that he said to Ed, "Why don't you take a sabbatical and go to Stockholm and work at the International Institute of Meteorology there?" And so Ed and his family did that for 10 months during the period of 1968 to 69. 2 years later, Ed chaired the Department of Atmospheric, Oceanic, and Space Sciences, this department having morphed from meteorology and oceanography into the inclusion of space sciences. John Leese is going to take some time now and talk about some of the graduate students that were there in those years, Ed's grad students. John?
Thanks, Gene. Ed was associated with the University of Michigan for a period of about 14 years. Now, my experience in working with Ed during the period 1961 to 1964 was similar to the other Michigan students who worked with Ed for their PhD after I finished. This experience was best summed up by Ed in this quote: "A finishing graduate student should be more current in his knowledge of the literature and the details of his subject, but that his mentor should be expected to be wiser." During my own experience working with Ed, 1961 to 1964, together with Roland Drayson, 1963 to 67, Rex Fleming, 1968 to 70, and Eric Pritchard, 1970 to 74, we find two common threads. First was Ed's encouragement for each of us to explore our own special interests. And second is the broad range of statistical applications for air pollution, satellite cloud images, and weather prediction. My personal experience involved the analysis of cloud images using two-dimensional spectral analysis. Since I was his first graduate student, I felt that Ed had difficulty understanding that I was so weak in understanding his conversion of the spectral analysis from 1 to 2 dimensions. I would ask Ed to clarify, and he would rattle off an oral thing, which didn't make any more sense than it had before, so I decided I would do a tactic of my own with a mentor in managing my mentor. I then made use of a tactic of focus on a specific part of the equations and informing him that I thought he had made a mistake. He would then proceed at great length to demonstrate on a chalkboard why he was right. From this I learned. Fortunately, he never asked me to show why I thought he made a mistake. In the summer of 1963, as I completed the plans for my PhD thesis, I was making real progress incorporating Ed as my mentor. When he informed me that he was taking a year's leave of absence to work with the Chief of the Weather Bureau and the Assistant Secretary of Commerce in Washington, D.C., I expressed a strong anxiety about his leaving and how it would affect my progress. He responded, "Oh, John, you will do fine." 1 year later, I finished my thesis and moved to Washington, D.C. for my first job. After I moved into my house, Ed came by to pick up my moving boxes for his use in moving back to Ann Arbor. Thank you.
Good. You two finished on that period, or where are we?
We're going to continue on from this. This is when Ed actually got Potomac fever in 1973. Bob White offered him a position as NOAA's, actually, this is the official title. He was the Associate Administrator for Environmental Monitoring and Prediction. And although GARP and its experiments were well underway at that time, all of those issues were under Ed's purview. But he relied mostly on NOAA and international staff people for it. But there was a new problem on the horizon, and it was climate. There were many national and international interests, and they were beginning to focus strongly on climate. And Ed, knowing what was coming and seeing what was coming, worked with Congressman George Brown to develop some legislation, which was passed in 1978 when Congress actually established a national climate program. Ed was selected as the director of that new office, and he ensured, among other things, that the Climate Analysis Center in the National Weather Service was given both research and operational missions. He also was involved in many of the international programs that were going on, and of course, eventually WMO and UNESCO actually created the IPCC. And the National Climate Program Office was deeply involved in all of this activity. It turns out there's another thing that I want to talk about, which is not directly NOAA, but involves NOAA. In 1972, Henry Kissinger, as our Secretary of State at that time, signed a joint agreement with the USSR on protection of the environment. And one of the working groups under that environment was called Working Group 8, and it was called the Influence of the Environment on Climate. There were actually 3 projects. One was a project on heat balance, one was a project on pollution, and another was a project on changes in solar activity. This was great from Ed's standpoint because he was involved in all of these issues, and in fact he'd even done some research in some of them. Part of that working group was to have interchanges between the U.S. and the USR scientists every year, and to have meetings of symposia, working groups, working groups. And one of those that strikes me something to be remembered was in 1978, the symposium was held in Dushanbe, which is the capital of Tajikistan. Now, the host country, in this case the Soviets, always wanted to be sure that the U.S. delegation saw something that was different. In this case, there were trips made to Samarkand and Bukhara. And this is great from the U.S. scientist standpoint, because not only did they see a lot of history on the old Silk Road, but they also had a chance to purchase things. And that's what I remember, is Ed Epstein coming back from that symposium with a rug thrown over his shoulder as he got on the plane. And Alice says they're still using the rug. So that was that was fun. Ed formed a very solid working foundation with Working Group 8. It's one of the few working groups that the U.S. can be very proud of because in all the time with the ups and downs of the Cold War, there was never a year when there wasn't an exchange between Soviet and U.S. scientists. Every year up through the 1980s. So, now John Zillman is going to talk about another international experience.
My interaction with Ed was from Australia, interacting with the US, mainly in GARP, early stages of GARP, and the climate program. But I'd like to just recall one very specific thing was very early in my period of involvement in international meteorology, and it had a profound impact on the whole future of Australian involvement in the international scene, and in particular, I think I could say, on the success of the Southern Hemisphere part of the global weather experiment. It was 1974 in Australia. It had followed a decade of very strong Australian involvement in World Weather Watch and the early stages of GARP. And the director of the Australian Bureau, Dr. Bill Gibbs, had at that point fallen completely out of favour with the upper echelons of the incoming Australian government. Indeed, he, as first Vice President of WMO, he was refused approval to even attend sessions of the Executive Council. Early plans for strong Australian support for GARP and the Global Weather Experiment, FIGI, were very much out of favour. We were very concerned that the Japanese planned to launch a geostationary satellite, which we had earlier strongly supported and were now told we couldn't be involved with, that would discourage the Japanese. And at this time came strong pressure from the industry in Western Australia, the offshore oil and gas industry, on the impact of tropical cyclones on their operations off the coast. Pressure on the federal government such that a conference was convened, largely sponsored by industry, but attended by the Premier of Western Australia, the responsible federal ministers, and in particular the key Commonwealth federal officials who were strongly opposed to the Bureau's involvement with Japan on anything to do with satellites, and in particular, I guess, anything to do with involvement in international programs like GARP. Ed came as a representative of Bob White. The invitation, for, I think, at close to Prime Minister level to the US to send somebody to help Australia better manage its warning systems for tropical cyclones off the northwest. I remember Ed clearly as almost as jet-lagged on that occasion, at least in the first day or two, as I am now, and he gave a great presentation on the US approach to hurricane warning and lessons that might be learnt in the Australian scene. And I watched him judging the body language of Australian industry, listening to just what were the issues that might help Australia in this way, and there was a lot of a hidden agenda just below the surface, and it was, could we somehow persuade, or would industry be interested in persuading the government that the government agency, the Bureau of Meteorology, should become involved in helping the Japanese, the Japan Met Agency with their geostationary satellite program. And it wasn't until the final session, a final panel session, where Ed saw the opportunity, and I've retold this occasion, happening on many occasions, because it was absolutely completely changed the character of the whole meeting, and indeed changed the whole Australian attitude to international involvement. Ed judged his his moment of intervention perfectly. He made the point first that in the US that the geostationary satellite was the first line of defence against tropical cyclones, and then I've got almost exactly his words, and I was involved in transcribing them into the final report. And he, in a somewhat delicate political environment, he made the point: Australia has much more to gain from participation in GARP than countries in the Northern Hemisphere. One of the objectives of the Global Weather Experiment, FIGI, is an optimum observing system that you will need for all purposes, including cyclone warning. The US can't do it all. International support is essential. The Japanese have undertaken, with help, to launch a satellite. Australian participation in the Japanese satellite program will ensure its success and encourage continuation into the future. Ed began very hesitantly in that intervention, as I recall it, and his final words were about as powerful as they could be. And immediately after that, there was a meeting of the key industry figures with the senior bureaucrats. Within 6 months, we had not approval but instruction to begin developing a bilateral agreement with Japan on how Australia might be able to support with ground turnaround ranging stations for the GMS, and within a year we had support for a major Australian participation in the Drifting Buoy program for the Global Weather Experiment. That was in the very early days of my involvement in national meteorology. I saw Ed's intervention on that occasion as completely turning around the Australian government approach to participation in the international scene. I think it had an enormous impact, and it's one of the things that I've retold many times as one of the great positives of collaboration between our community in doing good things.
Yeah, and I might add, you know, that made it possible that John had a job, and he then could become the head of the Bureau of Meteorology, and later president of the World Meteorological Organization and so forth, and president of their academy, etc. He's been no short of jobs, all because of it. Anyway, so we'll now turn to Bob here, and you're going to work more from the Climate Analysis Center forward, right? You want to stand here? Would be better off?
No, that's not necessary. Can you hear me? Yes, you can. I first met Ed Epstein 43 years ago at this meeting. I was a clueless graduate student participating in a panel discussion on meteorological education. I knew who Ed Epstein was, sort of. John Dutton made me read Rex Fleming's thesis. But my strongest impression from that panel discussion was how comfortable the senior professor from the University of Michigan made me feel. And of course, this was just Ed Epstein being the consummate gentleman that Epstein was. We didn't really cross paths again until about 10 years later, when Ed shifted from Rockville over to the World Weather Building. Then we started to see each other quite frequently. This is actually one of the meetings Ed started to go to probability and statistics meetings, and this was the one in Hot Springs, Arkansas in 1983. And that's a lot of Penn State and Michigan all mixed up in this hot pool. And you can look at it your convenience. It's in the brochure that Bob prepared. Wonderful memory. And this was very shortly before Ed joined the Climate Analysis Center. I believe that was in sometime in 1984. The Climate Analysis Center, I think, was a very special place to be in the 1980s. In my opinion, I don't think there was a comparable sized group studying doing the diagnosis and prediction of climate variability on intraseasonal interannual timescales that did research over the course of a decade that had more impact than what came out of the Climate Analysis Center in the 80s. Ed, of course, contributed to that greatly. During that period, I believe he published 8 refereed papers, and his book came out as well about 1.5 to 2 years after he joined us. I was privileged to be one of his proofreaders in the final stages of that process. So I think I'm as familiar with the book as Jim Elsner is. I was pleased he talked about it. Almost all those papers are being discussed by either Dave Unger, myself, or Dan Wilkes. I might mention one that isn't. It's a very important paper, in my opinion. I've used it a number of occasions in my career. Was with, of course, one of Ed's mentorship stars, Alan Murphy, and it was on the NWP types were always using a thing called the anomaly correlation in their beauty contests, their skill comparisons and skill analyses. And Ed and Alan did this paper where they really laid out how to correctly do this, because many of them weren't doing it correctly, and showed how the anomaly correlation precisely related to other performance measures. And of course made the point that the modelers should be looking at all aspects of performance, not just the association of one field to another. So Ed was extremely productive while he was at CAC. But the success of Ed did something perhaps maybe even more important to enable the success that and impact that CAC research had during the 1980s. Gene Beerley has already alluded to the fact that when, as one of the architects of the National Climate Program and the Climate Analysis Center, Ed helped ensure that CAC was set up with both operations and research. It was a very, obviously the people at CAC during the 80s made a big difference, but this marriage of operations, seasonal forecasts with mission-driven research was really very important to the synergy and the results of the things that were going on there. After CAC was formed, that wasn't the end of the story as far as the bean counters in Rockville and NOAA headquarters were concerned. This was a concept they didn't like, and they wanted to undo it. By the way, I'm relating Don Gilman's firsthand knowledge of that period. Don says that, Don told me that the only reason they weren't successful, that the research arm of CAC wasn't decoupled from the operations, was the advocacy of Ed Epstein during that period. He had the ear of Bob White, and of course was extremely well situated, well respected in the climate community. So we all owed Ed a very, very large debt for that. At CAC, of course, Ed was, practically the perfect colleague. He was patient, he was attentive, he was respectful, he was generous with his time and ideas. Hoog van den Doel describes him as maybe the perfect employee, but perhaps not perfect. Ed wasn't a pushover. And this is a little anecdote that Hoog reminded me of. We got a new director at the Climate Analysis Center after Jim Rasmussen stepped down. And we'll go unnamed for the moment. But he called us together for a staff meeting to lay out his ambitions and so forth. And he described his major goals for the next 5 years. And one of them was doubling seasonal forecast skill. Ed said in a stage whisper, "Oh, you mean from -2 to -4?" And he was speaking with authority because he had done the careful verification of our seasonal precipitation forecasts. Excuse me, just lost my voice. I think on that note, I'll pass it back to Dick, and if there's time, I'll tell another story.
Okay, we were trying also, they've been kindly very brief, but interesting, I think. But we wanted to try and have some time for you people to throw out a comment or two from the audience, and then also for allow them to engage back and forth. And I'm just going to start that by saying with what Bob said, that guy that he wouldn't name that came in as a new director, and I could tell that he wasn't totally happy with it. I'm a little concerned I might have selected him. Now, yeah. Anyway, something first. Someone want to bubble up from out there? Otherwise, I'm going to have these guys go at each other. So.
I wanted to elaborate a little bit on one of the statements. I didn't get a chance to talk about Alan Murphy. But Alan Murphy was a key person in Ed's life. Not only was he a doctoral student under Ed at the University of Michigan, Ed told me that when he came to Michigan, he had a whole series of issues he was working on. He had worked on stratospheric ozone. He was still trying to work with that. As John Lee said, he was working with the Pyros data. He was getting involved in some of the engineering applications with Houston and Gil doing one of the aero allergens project. I think, Gene, you said that was the big project that brought him there. But Alan Murphy, a graduate student, a very special graduate student, basically made it clear to him that it would be better if he focused on statistical work. And I think that happened like in 1963 or 64. I think in 63 he was in Washington, but in 64, Alan Murphy, a graduate student, had a key part in pushing him in the ultimate direction.
Bob, you want to comment?
I do. I didn't have a chance to say this, but Alan Murphy, of course, is a shining star that was mentored by Ed Epstein. And they were lifelong friends. And that's actually another anecdote I wanted to pass on to you, especially to Alice. You know, I think Ed was happy at CAC. But we remember a time when he was especially happy, and that was, I think, in the early 90s when Lev Gandine was around and Alan came for a sabbatical. And all three of them would gather together in the middle office looking over the parking lot every day at lunch and talk about the things that they talked about. One of the things, Bob, was, of course, arguing about the value of probability forecasts because Lev was on the other side. But that was that was a good period for Ed, and to see those three giants all sitting there together in that office was even a thrill for me.
Way in the back. Oh, Alice, it's you.
Alan Murphy and was very good friends. He talked about graduate students. Alan Murphy was his first graduate student and his last. It took that many years for Alan to get his PhD. Ed had to threaten him to cut off money, do all sorts of things, but he eventually did get it.
Okay, we don't have much more time, but is there something from out there or something from the panel? Yeah, John.
Just a nice little link again with Australia through Alan Murphy. Our regional director in the Australian Capital Territory, Ian Mason, spent 6 months or maybe 9 months working with Alan in the States and came back absolutely committed to the idea of introducing probability forecasting, probability precipitation forecasting in Australia. The rest of us were totally opposed. We eventually agreed that Ian could introduce for a trial period of 3 months in the Australian Capital Territory. I've forgotten the detail now, but as far as I remember, that trial went on for about the next 15 or 20 years. We weren't game to stop it, but we couldn't expand it nationally because my generation were again it. It's in now.
Good, John surrendered. Is there one more, and that's it? No more? So, oops, there's one.
Yeah, I'm Pete Lamb, and I became a rather young chief editor of the Journal of Climate when it started. And Ed, I think, who was an associate editor, he had previously been chief editor of the Journal of Applied Meteorology almost 20 years earlier when he was quite young. And when I had a conversation with him about it, he just sort of looked at me and said very quietly, "You'll spend most of your time examining mediocre papers." And it's often not fun, meaning that the very good ones will take no time, the very bad ones will also take no time. And he was exactly right.
Which ones are which category were your papers in? Anyway, I think we've run out of time. We're almost caught up for you, Bob, and thanks to these four gentlemen here for providing a little bit of history and a little bit of fun. Thanks. Bye.
Okay, for the last paper of this session is by Daniel Wilkes. I think you probably don't need to introduce him. He actually studied under Alan Murphy, and I guess got his degree under Alan Murphy, which I didn't know. Who, of course, got his degree under Epstein. So there's a direct link there. He's professor in the Department of Earth and Atmospheric Sciences, Cornell. And most importantly, he's the author of a book which, if you don't have it, you better sit next to someone who does. Statistical Methods in Atmospheric Sciences, the 3rd edition. Extremely good. And
great Christmas presents, folks.
What?
They make great Christmas presents.
Oh, okay. Great Christmas. And the title of his talk is Probability Forecasting, Quantitative Decision Modeling, and Economic Value of Forecasts.
So thanks, Bob. I first was exposed to this material, probability forecasting and decision modeling, from my PhD advisor, Alan Murphy, who, as Bob just mentioned, was Ed's PhD student. So that makes me Ed's academic grandchild. As far as I know, I'm Ed's only academic grandchild. If there's somebody else out there, I'd be interested to know about it. But that's quite a distinction, I think. Pleased to have it. So my remit here, probability forecast and optimal decision making, are intimately related. I like this quote from Bob Glahn, who emailed it to me in the process of persuading me to come do this talk. Using probability forecasts in decision making is what it's all about, right? Of course, Ed knew this. And that's a good quote. He did know that. So the two take-home messages I'd like you to have by the time I'm done here is first that probability forecasts impart more economic value than do non-probabilistic forecasts. And part of the reason here is that probability forecasts allow for separating the roles of the forecaster on the one hand and the decision maker on the other hand, and that's a good thing from the perspective of both. So to back up a little bit, uncertainty about the atmosphere is a consequence of sensitivity to initial conditions, what's called chaos. And the first couple of talks in the symposium here dealt with Ed's major contribution to that, his TELUS paper on stochastic dynamic programming. I reread that for the first time in about 30 years in preparing for this, and it struck me that there's a passage there that, as far as I can tell, is the earliest written description of ensemble forecasting as we know it today. And he wrote, discrete initial points in phase space are chosen by a random process such that the likelihood of selecting any given point is proportional to the given initial probability density. For each of these initial points, i.e. for each of the samples selected from the ensemble, deterministic trajectories in phase space are calculated by numerical integration. And I think what's key here and what distinguishes this description from ordinary Monte Carlo integration is that the initial points were thought of as random draws from an initial uncertainty PDF in the phase space. He didn't emphasize this in the paper. He just did the Monte Carlo integration as a source of verification data for the main point of the paper, which was the SDP. And that's where the last bit of the quote here comes from. After doing what we now know as ensemble forecasting, he computed means and variances corresponding to specific times by averaging the appropriate quantities, and that was his verification data. Okay, so to probability forecasting. Here's the extremely selective history of probability forecasting. In the late 18th century and early 19th century, Dalton and Lamarck used qualitative verbal expressions of uncertainty in weather. Cook, in 1906, was making non-probability forecasts, but he attached a sort of 1 to 5 rating to express his confidence in the forecast, and you could go back and map those to probabilities. In 1920, Hallenbeck appears to be the first person to produce probability forecasts in a modern, recognizable form, basically associating a probability, a real number from 0 to 1, with a specific, well-defined future outcome. In the mid-1950s, the Travelers Weather Service, which was a private forecasting operation, and the U.S. Weather Bureau, which is the predecessor to the Weather Service, began experimental probability of precipitation forecasts. These are point forecasts, probabilities of at least 1/100 of an inch of precipitation at a particular rain gauge in a defined time, experimentally at a couple of West Coast cities. And in 1965, this program went operational across the country. So when this program first got going, people were a little unclear about what the meaning of these new probability forecasts were. And in 1966, Ed produced these two papers that addressed exactly that issue. The quote at the bottom is from the second paper here. He wrote, "Probability statements are more useful than the conventional forecast to a broad segment of the users of the forecast. The evidence for this is so clear that the wide use of probability statements would have occurred much sooner were it not for uncertainties regarding the use and interpretation of these statements on the part of the public, and especially on the part of the meteorologists who must use them." So one of the confusions about the pop forecast, and the confusion seems to persist today, is do they pertain to points or do they pertain to precipitation over an area? And this first paper, point and area precipitation, addressed the relationship of the two, in part to aid forecasters. So here's a figure from that paper. He constructed an idealized model in which we've got some point location A within some larger area, unit area, that's the solid circle. And we've got these little rain cells of area Q. They their number density is N per unit area. The rain cell area is Q. And so any cell centered within the little dashed line produces point precipitation. Any cell centered within the larger dashed circle produces area precipitation. So Ed invoked Poisson distributions for the probabilities that one or more cells overlap either the point or the area, yielding the point precipitation probability, which is the upper equation, or the area precipitation probability, that is the second equation. And these, of course, both depend on the number density of rain cells and the area of the rain cells. But if you combine these two, you find that the relationship between the point probability and the area probability doesn't depend on the number density of the cells. It just depends on the size of the cells. And if you look at this equation a little bit, you see that if the size of the cells Q is large, the point and area probabilities are very similar. So this would be large synoptic scale rain systems. And if the size of the small cells is very small, then the point probability can be a lot less than the area probability. So another thing Ed did in this paper, as an aid to forecasters who might be able to think about the area density of rain cells, was he derived this equation for estimating point probability based on a probability distribution for the size of the rain cells. So invoking an exponential distribution for the uncertainty in, the number of rain cells, produced this expression for the expected value of the point probability, assuming that the forecaster could make a good estimate of the characteristic rain cell size. Okay, on to the second 1966 paper, the one entitled Quality Control. This addresses the meaning of the new probability forecast, the operational pop forecasts. And by meaning, I'm addressing what's called reliability or calibration of the probabilities. So if the forecaster says 50% chance of rain, what does that mean in terms of the odds? Does it really mean that an even money bet would be a fair bet? And in 1965 and 1966, this was not at all clear, not even to people who certainly knew their way around this as well as Ed did. So in true Bayesian form, Ed posited beta distributions for prior probabilities for the meaning of pop forecasts. So he parameterized the beta distributions in terms of the mean, assuming that the mean of the prior would be the same as the stated pop forecast, leaving the other parameter to be what he called a confidence factor, called it capital L. And the figure here is from the paper, illustrating some example prior distributions. Now, what's remarkable to me is that, as I said, Ed knew as well as anyone what was up with this format. And in his paper, he writes that his judgment seemed to correspond best to L equals 10. So if you look at the set of middle densities here, the one labeled these are for 50% pops. The one labeled L equals 10 is the second highest and therefore the second broadest. So what he's saying is that as of the mid-60s, when his interpretation of, without seeing any verification data, his interpretation of what the forecaster meant or what could be inferred from the forecaster saying 50% probability was that the probability was almost certainly better than 5% and almost certainly less than 95%, but probabilities anywhere between 20 and 80% were entirely plausible. So no wonder the public was confused. You would update these things with verification data. So the prior mean and variance I have at the top there, you would update these parameters to a posterior distribution after seeing, say, n forecasts of a particular pop, say 50%, which yielded R precipitation occurrences, and those are the expressions for the mean and the variance. So, for example, if we're taking Ed's prior for 50% pops with L equals 10, and we saw 10 more forecasts of pop equals 50%, of which 5 were followed by rain, we would update that initial prior to the posterior that shows L equals 20 and rho is a half, which is still pretty broad. But the thing is that for large verification samples, and we have large verification samples, the mean of this distribution for what is the meaning of a pop forecast converges to the relative frequency of the outcome, and the variance shrinks as 1 over n, regardless of what your prior distribution is. The implication is that probability forecasts can be taken at face value. That's the variance shrinking to arbitrarily small values. In quantitative decision making, given the large available verification data samples, when they indicate that the pop forecast matches the subsequent relative frequency to good approximation for each forecast value. And that is indeed what we have. Here's an old data set with forecast probability on the horizontal and subsequent observed relative frequency on the vertical. This is 2 years of data from the late 70s, and the calibration is really superb, with the exception of perhaps a little over forecasting for the higher probability. So really these operational pops can be taken at face value for operational decision making. So this brings me to the second part of the talk, the use of Bayesian decision analysis in meteorology. And this was introduced to the field by this paper of Ed's from 1962. The quote I have here is from Alan Murphy. This is I guess a semi-famous quote, although I think it's underappreciated by a lot of people, maybe forecasters especially, who are sort of know intuitively that what they do is valuable. But Alan pointed out specifically that weather forecasts possess no intrinsic value in an economic sense. They acquire value by influencing the behavior of individuals and organizations whose activities are sensitive to weather conditions. And the way one can analyze the best influence of the forecast information on decisions is through this approach of Bayesian decision analysis. So let's see. As I said, this topic was introduced to our field by its 1962 paper. It's a quantitative and I think underappreciated way to link forecasts and their optimal use. Brings some other benefits. It provides an approach to computing economic value of forecasts in particular settings. And it allows estimation of the economic value of hypothetically improved future forecasts. So it can help guide potentially where to exert effort in improvement of forecasts. So this is a pretty full slide, but it lays out the elements of a decision analysis. First, you need to define a set of available actions. call them A, and there has to be at least two. If there aren't at least two actions, then there's no decision to be made. You need to define a set of relevant events. I'm calling them X. Sometimes these are called states of nature. And in our business, these are meteorological events. And again, you need at least two in order for the analysis to be meaningful. You need probabilities for the events, and these come from weather forecasts when the events are weather events. Call those probabilities F. I'm assuming that they've been rounded to one of some number K, capital K probabilities. So if we're rounding probabilities to tenths, K is 11. So the probability is 0 or 0.1 or 0.2 up to 1. If we're thinking about operational pomp forecasts, which are very well calibrated, the conditional probability of our outcome X given one of these probabilities is exactly the same as the probability that's forecast, which is to say that calibrated forecasts mean what they say to good approximation. It's not required that you have good calibrated forecasts to do a decision analysis. We do in terms of weather forecasts. When you don't, you can get these conditional probabilities as Bayesian posterior probabilities. And finally, the outcome function, a given decision maker will have their own particular outcome function. Each possible combination of capital I actions and capital J events, so I times J possible outcomes, is quantified, and there must be preference order among these outcomes in order for the decision to be meaningful. If the decision maker doesn't care what happens, there's not much point in spending time worrying about the decision. Often these outcomes are measured in dollars. That's most straightforward and easiest. But there are other ways to do this too. Okay, so here's the general structure for a single-stage decision, which is one decision made in isolation that is not affected by similar decisions that might come before or after. I've got two slides here. This is the first of them. So each of the possible forecasts, there's some optimal action, and optimal means that it maximizes the expected outcome given the forecast. So this is a sum over the possible outcomes given the forecast for each of the forecasts, and the action I that maximizes this is the optimal action for that forecast. And the overall expected return from using the forecast depends then, in addition, on how often each of the possible forecasts F is used. So there's an additional expectation here in the middle over the frequency of use of the forecasts. These equations show that optimal use and valuation of forecast requires comprehensive, what we call diagnostic verification. In particular, that you can't just look at a single number summary, a mean squared error or something, and get a meaningful read on how useful or valuable the forecasts are. You need to look at the full joint distribution of forecasts and observations through its calibration refinement factorization, so that's at the bottom. The joint distribution of forecast F and outcomes X can be expressed as K conditional distributions for the outcome probability given each of the forecasts Fk. That goes into the expectation, the first expectation at the top of the screen, and the second element of the calibration refinement factorization is the refinement distribution, the frequency of use of the forecasts, that goes into the second expectation. Economic value forecast is computed as the expected return relative to the expected return from some baseline naive information source, which might be a constant climatological probability. So the implications of this are that forecasts can achieve non-zero economic value only if some of the optimal decisions associated with them are different from the default, the baseline decision that you would make, say, with climatology. Another implication here is that different decision makers will have different outcome functions and so may well derive different levels of economic benefit from the same forecast. Okay, so let me illustrate this with what's got to be the simplest possible decision setting. It's called the cost-loss ratio problem, although the lessons you draw from this generalize to more realistic problems. So this is the minimal decision problem. It's got two events. We call them adverse weather and no adverse weather. Decision maker has two actions available. One is protect against the adverse weather and the other is do not protect. And the setup assumes that when you take protective action, it costs you some amount C, but it's fully effective against the adverse weather. And if you don't take protective action, when the adverse event occurs, you incur some loss L. And if you don't take protective action and the adverse weather doesn't occur, then you lose nothing. And so the outcome function here is shown at the bottom in this little table. So the optimal actions, when we've got calibrated forecasts here, lead to you need to balance the protection action and the do not protect action. For the protection action, your expected outcome is minus C. You know that with certainty because regardless of what happens, it costs you C. If you don't protect, you incur loss L with probability F, that is the probability forecast because they're calibrated. And so the optimal action for any of the K forecasts is maximizes these two things. And you do a little algebra and you find that you take the protection action if the forecast probability is larger than the ratio of the cost to the loss, and you don't protect if it's smaller, and that's of course where the name cost-loss ratio problem comes from. Computing forecast value, you need to have a distribution of the frequencies of use of the different probabilities, the refinement distribution. So I've just made one up here. So I'm rounding probabilities to tenths, so there's 11 possible forecasts, and I've made up this distribution of frequency of use among them. If these were pop forecasts for tomorrow's rainfall, these wouldn't be very good forecasts, but I'll just be able to carry through an example. I have constructed these so that calibrated forecasts, which I'm going to assume they are, reliable forecasts, brings with them the implication that the climatological probability for our adverse weather event is 0.3. So if we are the naive decision maker without access to forecasts, we will take the protection action if the ratio of cost to loss for our particular decision is less than or equal to 0.3, and we'll take our chances with the loss if the protection cost is relatively expensive. If it's more than 3/10 of the loss. So the solid curve here, just pay attention to the solid curve here. I'll get to the dashed curve in a couple of slides. Shows the expected forecast value given optimal use of the hypothetical forecast. And because these are optimal decisions, the forecast value is non-negative for all decision problems. That's all cost-loss ratios. For very high cost-loss ratio or very low cost-loss ratio, the value goes to 0 because at those extremes, the decision is obvious without the use of forecasts, whether a good forecast or climatological forecasts. And the economic value is maximized when the decision maker's cost-loss ratio is equal to the climatological probability, because there the climatological information is least informative. Okay, why are probability forecasts more valuable than non-probability forecasts? Here's a quote from Ed's 1962 paper. In any discussion of the role of weather prediction in the decision process, it must be kept clear that there is a duality of roles. The meteorologist analyzes and evaluates the present and past weather and estimates the future state of the weather. The entrepreneur or other user of the meteorological service must be able to evaluate these predictions and analyses and translate them into the most favorable or desirable course of action. A lot of why probability forecasts are more valuable is that they allow the decision maker to think on his own rather than just take the forecaster's word for it. So if you're a forecaster and you are required to make a non-probability forecast, you know that the situation is uncertain, otherwise it would be a trivial task to make the forecast. You've got some internal probability for the occurrence of the event, and if you have to forecast yes or no, you're going to forecast yes if your internal probability is greater than some threshold value, P star, and you're going to forecast no if your probability is less than that threshold. Ideally, this threshold should be consistent with your user's decision problems. But the problem is that your users are almost always a heterogeneous group. They have different decision problems. They have different enterprises. They have different contexts. And some users, therefore, are going to be better served than others if you just choose one threshold. So in the examples, I'm choosing two plausible thresholds. I'll use P star as the climatological probability of 0.3 for these forecasts I made up. And also I'll look at what happens when P star is 0.5. Forecast yes if the forecaster thinks it's at least as likely as not. So in the context of the cost-loss ratio problem, all the decision maker knows when he hears a non-probabilistic forecast is, well, if the event is forecast, I better take protection. If the event is not forecast, I don't need to take protection. So if the protection is done, the cost is C. The cost is L with these probabilities that I've listed at the bottom from the frequency of use of forecasts. If the threshold probability is 0.3, the decision maker is going to take the loss with a 3.6% probability. If the decision threshold is 0.5, the decision maker will take the loss with 8.8% probability. And these are specific to the numbers I made up for that refinement distribution. All right, the dashed lines are the expected forecast values for the non-probability forecasts. The long dashes are for the 0.3 threshold. The dash dot are for the 0.5 threshold. And they are never more valuable than the probability forecasts. They are equal in value to the probability forecasts for cost-loss ratios equal to the threshold. And they are everywhere less valuable than probability forecasts for all other decision problems, all other cost-loss ratios. And sometimes the value can be very bad. Sometimes the value can be negative. Here, a lot of times the decision maker would be better served to ignore the non-probability forecasts and just make their decision on the basis of the climatology. The problem is that this thresholding process loses information. It specializes the forecast to the decision makers whose cost-loss ratio happens to be equal to the threshold probability. And in effect, the non-probabilistic forecaster is usurping the role of the decision maker, making the decision for the decision maker, but without knowing the particulars of that decision maker's setting. Looks like my time is running short. You can extend this to more complicated decision problems, multi-period decision problems, that were described in this paper that Ed did with Alan Murphy. And in particular, they looked at sequences of decisions that were related in time and subject to autocorrelated weather events as well, which is kind of a hard issue. I've got some slides here. I certainly don't have time to talk about this stuff, so I guess I'll stop right here. To conclude, uncertainty is inherent because of the chaotic dynamics of the atmosphere. Probability forecasting is necessary to properly communicate the resulting uncertainty. And probability forecasts are essential for optimal rational decision making. They're essential for realizing the full economic value of forecasts, and they are essential to allow the proper separation of the roles of forecaster and decision maker. Ed Epstein understood all of this, and he understood it well before most of the rest of us did.
Thanks, Dan. Maybe one or two questions for Dan? Anybody? Yes.
I think all of this is true that a lot of us understand this now, but there's still so many people who don't understand it. And how do we get that across and how do we put that into practice? Do you have any thoughts, Dan?
The question is, yeah, Ed understood this, and some of us do now, but a lot of people don't. And how do I have any thoughts on how to better educate people at large? And well, I try to beat this kind of stuff into my students. Some of them are back there. Giving talks like this, I don't know. It's a puzzle.
Yeah, and it's been a puzzle for many, many years. Any other questions? Yes.
Yeah, in your examples, you're assuming that the forecasted probabilities agree with the observed probabilities.
Right, and empirically that is the case for a lot of weather forecasts.
It is for weather forecasts, but not generally for climate forecasts. And, how do you adjust the value of those forecasts given that kind of information?
Well, you can compute economic value assuming that the user takes them at face value, and they're wrong. You can use them optimally if you've got some verification data that allows you to basically do a recalibration, compute Bayesian posterior probabilities.